The simulation theory you've heard about is fundamentally flawed, and here's why. It overlooks the most complex, unpredictable, and ultimately beautiful part of our existence. For decades, the idea that our reality is just a sophisticated computer program has captivated scientists, philosophers, and late-night thinkers. It's a tantalizing thought. What if the stars above, the ground beneath our feet, and even the thoughts buzzing in our heads are merely lines of code running on some unimaginably powerful supercomputer? This theory, popularized by figures like Nick Bostrom, often frames our universe as a digital construct, a hyper-realistic virtual environment. And it's a concept that truly makes you pause and question everything. But here's the catch. The way we usually think about this simulation, the way it's commonly imagined, is missing an entire dimension, a critical piece of the puzzle. This makes the idea far more complex, beautiful, and perhaps even terrifying than we ever imagined. At its core, the simulation hypothesis proposes that our entire perceived reality, from the smallest subatomic particle to the vastness of galaxies, is an artificial simulation, perhaps run by a highly advanced civilization. Think of it like a video game, but with graphics so good you can't tell it's not real, or a truly immersive virtual reality experience. The appeal is obvious. It neatly explains many strange quirks of quantum mechanics, the fine-tuning of the universe, and even the possibility of life on other planets, all just variations in the code. We imagine the simulators as cosmic programmers meticulously crafting algorithms and data structures to create our world. This perspective, though, is overwhelmingly computational. It sees the universe as a giant spreadsheet, a massive database, or an intricate piece of software. It's a compelling narrative, especially in our increasingly digital age, where virtual worlds are becoming more and more sophisticated. But here's where the prevailing view starts to falter. Life, our life, your life, isn't just data. It's something far more dynamic, far more unpredictable, and governed by a set of rules and processes that a simple computational model struggles to fully grasp. Ignoring biology in our understanding of a simulated universe isn't just an oversight, it's a critical limitation. It strips simulation theory of much of its explanatory power and leaves many fundamental questions unanswered. If we're truly living in a simulated reality, it's not enough to simulate only the physics of the universe, the gravitational pull of planets, or the way light bends through space. For this simulation to feel real, to have us in it, it must account for the messy, evolving, conscious, and ultimately biological matrix that defines our existence. And once you start to factor that in, the scale of the challenge for these hypothetical simulators explodes exponentially. Imagine trying to build a simulation of our world. Most people jump straight to the physics: gravity, electromagnetism, nuclear forces, then maybe chemistry, how atoms bond. But then you hit a wall: life. Life isn't just the sum of its physical and chemical parts. It's an emergent phenomenon, a cascade of intricate biological processes that defy simple reduction. This is where the simulation theory as we currently understand it needs a serious upgrade. We need to integrate the profound complexities of the biological matrix into its framework. One of the biggest hurdles for any simulation, even a theoretical one, is the emergence of consciousness. What is consciousness? It's that vivid, subjective experience of being you. The feeling of warmth, the taste of chocolate, the memory of a childhood dream, the joy of a laugh, the sting of a tear. These aren't just data points. They are felt experiences, qualia, that seem to exist beyond mere computational processes. Current models, whether in artificial intelligence or neuroscience, struggle immensely to explain how consciousness arises from purely computational operations. We can build neural networks that recognize faces or translate languages, but can they feel? Can they know they exist? Biology offers a potential bridge, albeit a complex one. Our consciousness appears to be deeply rooted in the intricate dance of billions of neurons in our brain, firing electrical signals, releasing neurotransmitters, forming ever-changing connections. It's a symphony of electrochemical interactions, a biological substrate so complex that we're only just beginning to map its basic architecture. To simulate consciousness, then, would require simulating not just abstract algorithms, but the actual biological machinery, the brain itself, down to an incredibly fine level of detail. Think about it. Every synapse, every ion channel, every neurotransmitter molecule, perhaps even the quantum states within those molecules, would need to be rendered with staggering fidelity. Consider the computational cost. Simulating a single neuron in real time, accurately modeling its electrical and chemical activity, already pushes the limits of supercomputers. Now multiply that by 86 billion neurons, each with thousands of connections, all interacting dynamically. And that's just one human brain. The amount of data processing and storage required to simulate an entire population of conscious beings, each with their own unique subjective experience, memories, and emotions, would be astronomical. We're talking about a level of computational power that makes current supercomputers look like abacuses. It would demand simulating matter itself down to potentially the quantum level, where the fuzzy, probabilistic nature of reality would need to be perfectly replicated. This doesn't just increase the computational resources needed, it introduces entirely new challenges for the hypothetical simulators, demanding not just perfect code, but perhaps a perfect mirror of physical reality itself. Another critical aspect of life in our universe is its relentless, unceasing evolution and adaptation. Life isn't static. It's a dynamic river, constantly carving new paths. From the first single-celled organisms to the vast biodiversity we see today, life has been shaped by natural selection, mutation, and emergent complexity over billions of years. A truly compelling simulation, one that could produce us, cannot neglect this fundamental force. It's not enough to just populate the simulation with pre-designed creatures. It needs to include the mechanism by which those creatures change, diversify, and become more complex over time. But simulating evolution isn't like simulating a simple physical law. Evolution is inherently unpredictable, driven by random mutations, environmental pressures, and the emergence of entirely new biological strategies. How do you code for the unpredictable? How do you write an algorithm that can generate novel biological structures, complex behaviors, and entirely new species that no programmer could have foreseen? If the simulators tried to pre-program every evolutionary pathway, the amount of code would be beyond comprehension. It would be like trying to write down every possible conversation that could ever happen in human history. Instead, they would have to simulate the rules of evolution and then let it run. But this presents a terrifying dilemma for the simulators. Once you set loose the forces of natural selection and mutation, you lose a significant degree of control. Biological systems are famous for their emergent properties, behaviors, and characteristics that arise from the interaction of simpler components, but which aren't obvious from those components alone. Think of an ant colony. No single ant knows how to build a complex nest, but the colony as a whole does. The same applies to species and ecosystems. This raises profound questions for our hypothetical simulators. Do they actively guide evolution, intervening to ensure certain outcomes, like the emergence of intelligent life? Or do they simply set the initial conditions and accept whatever unforeseen consequences might arise? If it's the latter, they would need an immense tolerance for chaos and a willingness to let their creation take on a life of its own, potentially evolving in ways completely contrary to their initial design goals. The sheer complexity of accommodating the unpredictability and emergent properties of biological systems makes the underlying code exponentially more intricate and difficult to manage than any mere physics simulation. Finally, let's talk about energy. Replicating the complexities of a biological world demands far more than just sophisticated programming. It demands immense energy. Every biological process, from a cell dividing to a thought forming, consumes energy. Our universe is awash in it, powered by stars, chemical reactions, and geological forces. If our reality is simulated, and that simulation mirrors the energy demands of our biological universe, then the simulators would need to be tapping into truly colossal power sources. Consider the thermodynamic laws that govern our universe. Energy is conserved, it transforms, and entropy generally increases. If the simulation is truly high fidelity, it would have to perfectly replicate these laws, down to the energy consumption of every metabolic process in every living cell. Simulating the vast energy cycles of an entire planet, with its living biosphere, weather patterns driven by solar energy, and geological activity, would require an unbelievable amount of power. It's not just about running the code, it's about powering the simulation engine itself, which would be generating and processing all of this energy data. This isn't just a practical constraint, it necessitates addressing the very foundations of physics within the simulation framework. How do the simulators generate the equivalent of stars, black holes, and the Big Bang within their own reality? Do they have access to infinite energy sources? Or does the act of simulating such a complex, energetic biological reality drain their resources to an unimaginable degree? The energy requirements alone force us to reconsider the very nature of the simulators themselves and their own place in a larger reality. It suggests that if our universe is a biological matrix, then the simulators behind it are operating on a scale that beggars belief, potentially facing resource constraints that make our own energy crises seem trivial. So, when we update the simulation hypothesis to include the biological matrix, it transforms from a purely computational thought experiment into something far more profound, far more demanding. It's not just about rendering pretty pictures or running physics equations. It's about generating consciousness, evolving life, and powering an entire biosphere with all its intricate, energetic, and unpredictable processes. This isn't just a bigger computer, it's an entirely different beast. It asks the simulators not just to be brilliant programmers, but to be cosmic architects and, perhaps, even creators of consciousness itself. The traditional simulation theory, while thought-provoking, has often felt a bit cold, a bit sterile, focusing primarily on the digital scaffolding of reality. But once we introduce the biological matrix, the picture becomes vibrant, messy, and immensely more compelling. It forces us to ask deeper questions, not just about the code, but about the very nature of life, consciousness, and the unimaginable power required to bring such a reality into being. It implies a simulation so advanced, so intricate, so overflowing with emergent complexity, that it pushes the very boundaries of what we can conceive. This isn't just a simulated universe. It's a living, breathing, evolving, and conscious one. If this exploration of the biological matrix has your brain buzzing, then you definitely want to check out our next deep dive right here.